So I'm going to talk about two fairly interesting debris disk systems that have been observed by Herschel recently. I'd like to say thanks to the organisers for putting on this great conference that's run so smoothly, and also thanks to the speakers who've come before me this morning who have hopefully saved me quite a bit of time in this talk so we can get out to lunch on time. So I'd like to acknowledge all these people who've been working on this stuff with me. The debris survey with Herschel, which Jonty mentioned, and also a survey of nearby stars with Scuba 2, the Sun survey, which Wayne Holland has a poster on. I'll show one, admittedly just an upper limit from that survey. So I'll give a very quick overview of the surveys, given that Jonty's already discussed these, and then present these two systems. So Deltascope Doris is a relatively young quadruple star system with a nice hierarchy of orbits. And we've detected a second debris disk in this system, and we've got MIPS and PAX photometry for this. And there's also a background galaxy in the field. As Jonty was mentioning, these things turn up quite frequently in 160 micron PAX images. And the other system I want to mention is HD37594. Which seems to be one of the most massive debris disks around an A-type star within 45 parsecs of the Sun. So with these nearby star debris disk surveys we've been doing in the far infrared, we've had an overriding goal to sort of build up a minimally biased picture of how debris disk properties and incidence vary with different host star parameters, planetary systems, everything you could imagine. And so the obvious samples to go for this are volume limited samples. Has the advantage also, as well as including a wide range of different types of stellar systems, that the targets are nearby, so the far infrared fluxes from dust are maximized, and the chance of resolving them are maximized as well. So with debris, we're observing a little bit under 100 samples in each of 5 spectral type classes from A to M, so we have separate volume limits for each of these. And we put quite a lot of effort into compiling these samples before the survey, so that we were as complete as possible and fully took account of the membership of the systems in terms of multiple star components. So we now have between the various nearby star surveys, probably at least about 500 systems from A through M spectral types that have been observed with both MIPS and PAX. I'm not sure about the numbers. It's 446 is the total of systems in debris. So before we started the debris survey, we wanted to make sure we had MIPS observations of as many of our targets as possible. So for the Sun-like stars, this has largely been done already by other Spitzer projects. So we chose to concentrate a little bit on the A-type stars. There's a lot of work on A-type star debris disks done with Spitzer previously as well. But there was quite a few in our volume that hadn't been observed, so we put in a proposal and we got some time, and we were able to fit like most of the sample, and most of the debris A-star sample. So basically all the A-type star systems within about 45 parsecs of the Sun, which is about 130 systems. And with our little bit of observations for about 30 systems, we also reanalyzed all the MIPS photometry observations of other A-type stars in our sample. We took particular care of multiple star systems, so we used PSF photometry for doing the photometry to make sure we can separate components as well as possible, and making sure we got photometry for as many components in the systems as we knew of. So these surveys are all legacy surveys to provide statistics, but they obviously turn up some pretty cool systems as well. So particularly disks in multiple systems, quite a lot of work's been done on this. In the protoplanetary phase, it's quite common to have multiple disks in systems. Antonio Hales has a poster on a system in Chameleon, DX Char, which is a system of 5 stars with at least 3 detected protoplanetary disks in there, at least 2 of which we've resolved in the submillimeter. And also, Gaspar mentioned in his talk a few days ago these multiple edge-on disks that he'd nicely imaged. debris disk systems, more evolved systems, we know that we get circumbinary disks when you have stars with a small separation, just a few AU or less. And we know that you can quite often have a circumprimary or circumsecondary disk in a system that has a large separation, like at least 150 AU. But I don't think any systems previously known where you had 2 debris disks in one system. So this Deltascope Doris is one example of that, as I'll show. It previously was known to have a disk around the primary star, but nobody noticed there was one around the tertiary star. So Deltascope Doris, it's a quadruple system with a nice hierarchy of orbits. You have this triple system down in the lower left here, where you have an A-type, the A-type, A0 type primary star, and then roughly very late K, early M-type star binary pair with a projected separation of 160 AU. And then further away we have a tertiary component, but projected separation of about 3,000 AU. Unfortunately, we don't have orbits on this. And we have an age for this system because it's been recently confirmed as a member of the AB Doradas moving group. So here's the Spitzer MIPS image where we notice that you see it's bright at 70 microns on the right there for both components for both these groups of stars in the system. Well, actually, with the PSF thing, photometry at 24 microns, we can resolve out the secondary M-type stars and confirm that the excess is definitely around the A-type primary star. So here's what we get when we add in the Herschel data from the debris survey. So we've got 100 and 160 micron PAX maps. And I've made a composite here with those 2 maps and the 24 micron MIPS. And what you see is see the two systems, the AB there with the circumprimary disk in blue, and then over on the right we have the tertiary disk, which shows up a lot cooler in yellow with the flux distribution peaking around 100 microns or so, and also a galaxy on the left there, about 10 microns from the primary, and 10 arc seconds from the primary, and that 10 arc seconds puts it somewhat within the MIPS 70 beam. So the conclusions on this system previously have probably got a little bit of flux in the MIPS 70 point from the galaxy. So galaxy contamination, Jonty's already done an excellent talk on this. So it's very frequent at 160 micron that we get galaxies contaminating debris disks. And to some extent that's also got to happen at MIPS 70. The galaxies are fainter, but the beam is very large, about 21 arc seconds or so. So for this system we did a quick estimate of what the 70 micron flux of the galaxy would be, and we see it would be between 2.5 and 9 millijanskis. So in our SED modeling we subtract 5 millijanskis on the 70 micron point, which is about 10%, so it's not too bad. And here's the SED fit we have for this circumprimary disk. There's a few things to note. One is that it comes out being quite warm, about 158 Kelvin. And it's been identified in the literature previously as a warm disk, so that's not a great surprise. It also, as Jonty was saying, some systems seem to show quite an early fall off in wavelength. For the SED, it gets steep at maybe around 70, 80, 90 microns. When we have to invoke this as well here to model the PAX photometry. In the literature, this has also been identified as a system with multiple temperature dust components. And we think after you subtract off the flux from the galaxy on the 70 micron point, that's not very significant, but the IRS spectrum still doesn't agree perfectly with a simple modified black body as we've shown there. So here's the fractional residuals to the full SED fit, and the IRS is within 5% throughout the wavelength range, but there's definitely systematics there. The vertical dotted lines on there indicate the transition between the orders and the IRS spectrum that we've used, so you can see that there are some clear steps and things there. So I'm not sure how much we can read into having multiple temperature components in this system. And the tertiary disk, however, is much more like a typical isolated debris disk. It's like 70 Kelvin. and we can't constrain from the Herschel photometry where the spectrum starts to steepen up in the far infrared. It looks very much like your sort of stereotypical debris disk. Summary of the system: we have a circumprimary disk around an A0 star that's warm. Being warm means it's compact. Just 2.5 times the black body radius would give you 50 AU. It's relatively low mass compared to some of the other debris disks around A-type stars, and it has a steep far infrared spectrum. So the implication that this is likely to be at least somewhat due to dynamical interaction with this low mass pair at a separation of at least 160 AU, because we only have a projected separation. The primary star has a very high V sin I, so it's probably very much equator onto us. So any debris disk would presumably be rather edge on as well. A circumtertiary disk is very classical. So it's an interesting system because it exemplifies many of the things we know about, or we think we know about disks in multiple star systems. That you can have circumprimary ones when the separation is relatively large, so systems with separations of a few tens of AU, it's very, very rare to find a debris disk in there. So this is the other system I want to talk about. This star is interesting because it's not interesting, if that doesn't sound like too ironic. But it's a late A-type star, no known association membership, signs of youth, chemical peculiarities, signs of rapid rotation, pretty much everything. Except when we observed it with MIPS, it came out with 400 millijansky 70 micron flux, which is huge for a debris disk. The reason it had never been detected before is indicated by this beautiful image. 400 millijanskys at that wavelength should have been detectable by IRAS, but this thing is in Orion, so it's here. That means that IRAS is very much confused by all the clouds around it, so it wasn't seen until we detected it with MIPS. Unfortunately, this was actually included from the debris survey due to a cut-on predicted cirrus confusion. There's another image of it next to some nebulosity. So here's the full SED we got after we've got our Herschel data on it. So we've got basically 24 microns through to 500. By 350, 500 microns with Spire, it's getting a bit ropey. And we've also got a scuba 2 upper limit, which agrees with the predicted flux of the system. So here is a quick look at the PAX Inspire data that we got for this, which shows that there are quite a few other sources around there at the longer wavelengths, as we'd expect, given that it's in a confused region. The images, the PAX are very much resolved, so we've got some quick deconvolved sizes from that, which agree pretty much with what have been seen for other resolved A-star debris disks observed with PAX. The 160 micron seems to be somewhat larger and elliptical, and it's yet to be seen if this is a problem in the fact that we're stacking multiple observations, or that it's it's a confusion issue, or if it's actually something real. So Grant Kennedy has done some quick, we've attempted to do some quick modeling of the PAX images combined with the full spectral energy distribution. It'll be at least at the 70 and 100 microns, we can get a very good fit with a face-on ring with a diameter of about 130 AU, with some outward extension due to grains being blown out by the radiation pressure. 160 micron is not so great, so this is very much work in progress. So the thing that's kind of striking about this is not just its 70 micron flux, but just from the MIPS photometry, the implied dust mass is about the largest of any disk around an A-type star within 45 parsecs of the Sun, which is the volume of the debris survey. So it seems to be a similar mass to sort of Beta Pictoris and somewhat more than Fomalhaut. And the architecture as a face-on ring, as a ring with sort of maybe 130 AU is also kind of similar to Fomalhaut. So it's quite striking. But one of the problems with the system is we don't know its age. So it's very difficult to find the age of an isolated star, especially an A-type star. A few things we've got to go on. Isochrone fitting suggests that it's consistent with a zero-age main sequence, so it might be quite young. Although we've not done this very robustly yet, it looks like that just really constrains it to being less than about 500 million years old. It's a late A-type star, so it could live to a couple of gigayears. Also, the very low V sin I is a little bit suspicious, and we don't know what the real rotation is. I mean, if it's pole on, then it's going to look a bit bluer than it really is. And that may skew things from the simple isochrone fitting. In terms of its space motion, it's basically just heading straight away from the sun. It's not clearly associated with any moving groups. We need to do some more work on this. Yeah, it was actually quite close to the sun. 1.8 million years ago, apparently, although I'm not sure how well you can extrapolate that back. So, what can we do with ALMA on this, if anything? Incidentally, we're now commissioning long baselines. So there's 2 antennas on 1 kilometer baselines here, and we're now up to 3, and there's a few more going out as well at the moment. So we want to resolve the debris disks, especially in the sub-millimeter, so we can see where is the mass, and look at the dynamics, how the planetesimals are interacting with planets. ALMA can do that. It can also image any gas if present, as was shown for Beta Pictoris this morning. And if we get multiple bands, then we can get some SED information, resolved SED information, get some grain properties and temperature properties. However, the problem with debris disks is that in the sub-millimeter, they just tend to be faint. I mean, there are definitely examples that are bright in the sub-millimeter. And Wayne has a very nice poster on this, poster 6.18, with some of the examples coming out of the Scuba 2 Nearby Star Debris Disk Survey. But anyway, most of the sub-millimeter bright debris disks are either very young, like Beta Pictoris sort of age, or are extremely nearby, which is a problem for ALMA because they don't fit in the beam of the antennas, so you have to mosaic them. And HD 37594 is potentially a nice compromise in that it's got a reasonably large sub-millimeter flux, but it will fit within the beam of the antennas. So here was the Fomalhaut example, which has been shown many times throughout the conference already. To get this field of view, it actually requires some pretty potentially dubious correction. I mean, the field of view that they use in the paper is much larger than the 4/width half max of the beam of the antennas. So it's really pushing things. So to image Fomalhaut, you need a mosaic of many points to image the full disk reliably. So HD 37594, about 2 millijanskys in total, with a 1 arc second beam, which would be kind of nominal, and a nominal sensitivity, the emission spread over about 20 to 30 beams, then we would get a significant detection over most of the disks. So this is something we're really looking forward to trying, if possible. Can I get my summary back? Anyway, the summary was that we've detected we've got a system with 2 debris disks in it, and it has 4 stars in total. Lots of nice, orbital hierarchy there. So a nice example of debris disks in multiple systems. And we detected what seems to be about the most massive debris disk around an A-type star within 45 parsecs of the Sun, which is a very nice potential ALMA target. Cool. Oh, and yeah, be warned of galaxies, as Jonty said. So, thanks.
Great. Questions for Neil? Yeah, Jean-Charles.
So if I understand correctly, in your quadruple system, you have 1 disk around the primary and 1 disk around the tertiary, which is at the projected distance of 3,000 AU, right?
Yeah.
So my question, actually I have two. My first question would be, what's the extension of this disk around the C component? And if you have an extension, do you think it could be related to a truncation by dynamical effects, considering that it's at least 3,000 AU from the main primary star?
For that system, neither of the disks resolve, so the only implication we have over size is from the black body radius, which should put it at about around, it'll be, the black body radius is around 10 AU, so it'll be a few tens of AU, and it's a K1 spectral type star.
Okay.
I guess that's maybe smaller than some known debris disks, but it's not tiny.
Okay, but it's much shorter than the dynamical truncation radius you would expect from at such a distance.
Okay, yeah, I guess.
No, okay. And my second question, what about constraints for a disk around the B component? Do you have an upper limit? Maybe you mentioned it, maybe I missed it.
For the B component, the emission looked to be purely photospheric, but the only resolved photometry we have is at 24 microns. With the PAX photometry, we don't have the signal to noise or the beam stability to be resolving things at 4 arcsecond separation. So at 24 micron, it looks to be photospheric, but maybe there is something cold around the B component. Is hard to say.
Other questions? Okay, if not, let's thank Neil and all the speakers from this.